this video, we're going to use the mean value theorem in applications. It says if a stone is dropped from a height of 89 feet, its position after t seconds is given by the function s of t equals negative 16 t squared plus 89. Find the time guaranteed by the mean value theorem when the instantaneous velocity of the stone equals its average velocity over the complete fall. So first of all, we need to talk about what the mean value theorem states. The mean value theorem states that if f of x is continuous, so we're going to say if f of x is continuous, on AB, and f prime of x is differentiable on the open interval a to b. Notice it doesn't include the endpoints for what f of x has to be continuous on. Then f prime of c, so there's some value c that if we take the derivative of, f prime of c is equal to f of b minus f of a all over b minus a. So this is saying that the that the slope at some point c would equal the average slope, because that's what we're getting here, that we're getting the endpoints here, the average slope of the function. So we're saying this is instantaneous slope at c is equal to the average slope. So what we have to do is we have to figure out, is f of x continuous on AB? And then is f prime of x differentiable on AB? And then we want to figure out what the, for this problem, because they're saying when the instantaneous velocity, so they're trying to ask what's a v prime, they want to know v prime of c is equal to the velocity average. We're trying to figure out at what time. So we want this at what time? What time does this occur? Well, we can go about finding the average velocity by saying that the velocity average is equal to the distance at time, we're gonna call this s of t1, so time 1, minus s of time 2, all over t1 minus t2. So we're gonna say that time 1 is basically 0 seconds. So we're gonna say t1 is equal to 0 seconds. And we don't know t2 yet. So we know that we start at 89 feet and we drop a stone. So the picture here would be like 89 feet being dropped from some height. So this is an 89-foot drop landing here. And we want to find the average velocity for this piece here. Well, we know our initial time, which is 0, but we don't know our final time. But we can figure out our final time because we know that s of t represents the distance or the position after so many seconds of the stone being dropped. So if I set my position equal to 0, meaning it hit the ground, I can find t here. So I'm going to say 0 is equal to negative 16 t squared plus 89. So then I'm going to subtract 89 on each side. And I get negative 89 is equal to negative 16 t squared. Divide by negative 16, I get 89 over 16 is equal to t squared. And then I'm going to take the square root on each side. So I get t is equal to, when I take the square root of this, I get root 89 over 4, because the root of 16 is 4. And I don't have to worry about a negative here because I can't have a time which is negative. So now what I can do is I can go through and I can find the average velocity. So the velocity average is going to equal S of, this would be, actually I had these backwards. Time 1 is not 0 seconds. Time 1 should be, this should actually be time 2 minus time 1. I screwed that up. This is time 2 minus time 1. Got to take the second time minus the first time for each of these. So time 1 is still 0 seconds. I just had this formula backwards. So time 2 would be root 89 over 4 minus S of 0 over root 89 over 4 minus 0. So when I plug in S of root 89 over 4, into that equation, so I get negative 16 I'm going to take this equation, put it in the calculator, then I'm going to put this number in. So we're going to say root 89 over 4 and we get 0. So I have 0 here minus S of 0 would be 89 feet over root 89 over 4. So when I go ahead and start simplifying this, I'm going to get negative 89 times the reciprocal of this, so I'm going to take it times 4 over root 89, which is going to give you negative 89 times 4 over root 89. So I'm going to rationalize this denominator by multiplying by root 89 over root 89. And I end up with these canceling, the root 89s would make 89, and the 89s cancel, so I end up with negative 4 of root 89. So this is my average velocity, and the reason it's negative is because it's going downwards. Okay. Now what I want to do is I want to figure out the derivative for S of t, because I got to make sure that the derivative, this is a polynomial, so I know it's continuous on AB, but I need to take the derivative of this to make sure that it's differentiable on AB. So if I take the derivative of S of t, I would get S prime of t is equal to, that'd be negative 32t. This is a linear, so I know that we're good. It's differentiable on A to B. So now what I can do is I've basically guaranteed that there's a point where S prime of t is equal to the velocity average using the mean value theorem, because this is true, right? F of x is continuous on AB, and f prime of x is also differentiable on AB. So these two things are true, which tells me that this formula should be true, which means that for us, the instantaneous slope at C, which would be S prime of t, is going to equal the average slope, which is our velocity average. So I can go ahead and start writing this out. I can say that S prime of t, I'm going to write it right here. Just going to kind of make a... So I can say S prime of t is going to equal the velocity average. Well, S prime of t is negative 32t. and the velocity average is -4 root 89. So I can solve for t now by dividing by -32 on each side. And I get t is equal to, when I divide these, I get root 89 over 8. So the time where these two things are equal, the instantaneous velocity and the velocity average, this time where that occurs is at root 89 over 8, which if I put that in the calculator, I think they want an exact answer, but we'll get the decimal too. That's 1.18 seconds. And so we use the mean value theorem to find this value for t, for the time, which was 1.18 seconds. And so that's how you use the mean value theorem in applications.